Hi, today we'll talk about amino acids. As their names imply, there should be an amino group and an acidic group, which is the carboxylic group. These two groups are connected by a carbon atom which is connected to a hydrogen atom and a side chain group. That could be anything. The side chain is represented by the letter R. The first carbon connected to the carboxylic group is called the alpha carbon. Of course, the second one will be called beta carbon, the third gamma, and so on, depending on how many carbons are there in the side chain. Now we'll leave the amino acids for a while and we'll talk a little about stereochemistry. In nature, there are many molecules that are mirror images of other molecules, but they are not identical. So how could a molecule has mirror image and it's not identical to it? Well, let's see how's that. This shape has this mirror image. The same goes with this one. Our question is, are these identical or not? The answer is yes. This is because they are superimposable, which means that each of these shapes can fit into its mirror image. So why did I say that some mirror images are not identical? Let's see this example. My left hand's mirror image is my right hand. But what you should notice here is that I can't fit my left hand in my right hand. Someone may believe that he is clever and would turn his right hand and see that now his left and right hands are identical. Well, this is not correct for two reasons. The first is, you're now looking at your palm, not the back of your hand. The second is, because of your thumb's configuration. As you can see, your thumb is bent towards your palm. This means that you can't fit your left hand in your right one. So your hands are said to be non-superimposable images. In the Greek language, the word kyr means hand. This is where the word chiral came from, which is used to describe molecules that have non-superimposable mirror images. And of course, achiral describes a molecule that has a superimposable mirror image. In organic chemistry, in order to have a molecule with a chiral carbon, the carbon will need to be connected to 4 different groups, which is the case for any amino acid except for glycine, which has a side chain composed of only hydrogen atom. So the alpha carbon, which is the main of our focus, is not considered chiral in glycine. Now you should be introduced to the terms levorotatory and dextrorotatory, which come from the Latin words meaning left and right. Deciding whether an amino acid is levo or dextro is based on the similarity between the amino acid and L-glyceraldehyde, which is denoted levorotatory because the hydroxyl group is found on the left-hand side. L-glyceraldehyde has a non-superimposable image, which is of course D-glyceraldehyde. And again, don't try to be so smart and say if we turn the D-glyceraldehyde, it will be the same as the levo. Because if you did so, you will find that the corresponding groups are not lying on the same plane. Proteins are made of 20 different L-alpha amino acids. Of course, there are some exceptions in nature. There are D amino acids found, for example, in cell walls of some bacteria. In the description below, you'll find a couple of links to videos that will help you memorize the structure of the amino acids, which will of course help you in classifying them as polar, nonpolar, aliphatic, aromatic, etc. The carboxylic and amine group can be looked at as weak acids because both are capable of donating protons. First, let's have the Henderson equation in front of us. One thing I want you to keep in mind is that log anything that is less than 1 will be equal to something that is negative, and log 1 is 0, and anything above 1 will give you a positive value. You can pause the video and try some values. The first amino acid we'll titrate is alanine, which is an example for a dibasic amino acid. Dibasic means it's capable of donating 2 protons. The titration curve of alanine shows 2 zones where the changes in pH are minimal. This is because since it's a dibasic acid, it has 2 pKa's. For detailed explanation of such curves, you can watch the pH and buffer videos. Let's say we have a pH scale where 0 is at the left and moving right will be heading to 14. Now we'll see at different pH values what will be the state of the titratable groups, and what I mean by this state, are they protonated or deprotonated? The pH values will be 1, 7, and 13. The two pKa values for alanine are 2.4 and 9.9. 2.4 is the pKa for the carboxylic group and 9.9 is for the amine. What we're going to do is that at each pH value we are going to substitute our givens in the Henderson equation to see in which form our group will be, protonated or deprotonated. By substituting pH for 1 and pKa for 2.4, you should know by simple logic that this term should be something negative. This means according to the rule we agreed upon that A- over the protonated form is a value that is less than 1. So we can conclude that the denominator is the predominant form. So the carboxylic acid is found in its protonated form when the pH of the surrounding medium is 1. The same goes with the amine group. You should now keep in your mind that whenever the pH of a medium is less than the pKa of the group being titrated, this group will be present in its protonated form, and vice versa. So when the pH exceeds the pKa of the carboxylic group and rises up to 7, we'll have the deprotonated form of this group. But the amine group will stay in its protonated form since the pH of the medium is still below its pKa, which is 9.9. I guess it's easy enough for you to predict what will happen when the pH rises up to 13. What really matters to us is the net charge on the amino acid. When pH was equal to 1, the net charge was equal to positive 1, which the protonated amine contributed to. When the pH was 7, the deprotonated and protonated forms of the carboxylic and amine group cancelled each other. And when both groups were deprotonated at high pH, the net charge was negative 1. The next amino acid we'll titrate is histidine, an example for tribasic amino acids. The titration curve will have 3 zones where the changes in pH are minimal, corresponding to its 3 pKa's. RH represents the side chain. The pH values will be 1, 4, 8, and 12. The 3 pKa values for histidine are 1.8, 6, and 9.3. Here we'll do the same what we have done with alanine. What matters again is the net charge. When the amino acid bears no net charge, it's called zwitterion, and the pH of the medium is called the isoelectric pH, or simply pI. To calculate the pI for any amino acid, you will have to get the mean of the pKa values at which the zwitterion exists between them. For instance, alanine's pI will be the average of 2.4 and 9.9, and for histidine it will be the average of 6 and 9.3. Now we'll talk about the peptide bond, which connects amino acids to form peptides, and if there is a large number of amino acids, we'll have a polypeptide chain. In order to form a peptide bond, a water molecule has to be released, and the reaction is called condensation. For the reverse to occur, a water molecule has to be added, and the reaction is called hydrolysis. Since the bond between the carboxylic and amine groups leads to formation of a amide group, you can call the bond also amide bond. The distance between the alpha carbons is 0.36 nanometers, which is also 3.6 angstroms. Since the nitrogen has a pair of lone electrons, this can lead to formation of resonating structures, in which there is a double bond between the nitrogen and the carbon. This gives the peptide bond a partial double bond character, which means that there won't be any rotation around this bond. So the atoms surrounding the bond, including the alpha carbons, will all lie on the same plane. Before setting you free, you have to know that whenever a sequence of amino acids in a peptide chain is drawn, you will always have the N terminal on the left hand side and the C terminal on the right hand side. And when naming small peptides, you have to start from the N terminal, and you should replace the suffix ate or in with "-ile" in all the amino acids except the last one. Here is an example of a peptide formed of alanine, aspartic acid, and glutamine. It should be called alanyl aspartyl glutamine.